I think we can get started. I see there's still some people sleeping late, but I'm sure they'll join us. Any questions before we continue today? Okay, so today I'm going to be switching gears a little bit because we'll be talking a lot about modeling details today and in preparation for discussion of applications tomorrow. So the focus will be on spray combustion modeling. We'll talk about modeling of atomization, drop breakup, drop collision and coalescence, droplet processes such as drag, impingement on walls, and spend quite a bit of time on vaporization, and then discuss some of the other important aspects, heat transfer, and then emissions modeling, in particular nitric oxide and particulates. So, and then, as I said, tomorrow we'll kind of put everything together and talk about applications to engines. Okay, so as I say, today will be quite heavily focused on modeling details. So if you look at an internal combustion engine, I've just drawn a typical truck engine here where the bore is about 10 centimeters in diameter. And of course, we have direct injection of a spray. The spray droplets may be characterized by sizes on the order of 10 microns or so. You can see that if we wanted to resolve down to the level of droplets, we would need 10,000 grid points if we were doing a one-dimensional calculation, just to get down to 10 micron. But in a three-dimensional calculation, that would be 10 to the 12 grid points. And it's just totally impractical to expect that you could resolve down to the size of droplets in a spray. So that means basically that we're going to be requiring submodels to describe processes that occur on scales below the scale of resolution of your mesh. Typical mesh numbers that are that people are using in simulations these days, really the maximum you see is around 1 million cells. So we're definitely far away from what's required for resolution down to the level of droplets in a spray. And in fact, we're down to, if you consider also boundary layer thicknesses in engines and various other things that we'll discuss later, we're not able to resolve those either with typical mesh resolution. So we need submodels for a lot of processes. And that's what I'm going to focus on this morning. So droplet processes such as drop drag, droplet turbulence interaction, vaporization, atomization, the breakup of drops, collision and coalescence, and spray wall interaction are all things that are going to be modeled rather than resolved. Okay, so let's see how we would go ahead here. We're interested in a multi-phase flow problem. We have the gas phase, and then we're spraying a liquid into that gas phase, so we're interested in describing the liquid phase. And then, as always, since engine flows are generally turbulent, we have to deal with turbulence. If you look at the two-phase flow regimes that are encountered in a typical diesel application, for instance, you have an injector nozzle here where you're injecting some liquid. It's close to the nozzle, very optically dense. In fact, there's a lot of controversy about what actually happens to the liquid in this so-called churning region. Optically thin, as I said. As you move further downstream, the spray tends, because it's in training air, tends to broaden. The optical density decreases, and eventually you have what's called a thin, optically thin spray. And then finally, very thin. And here you may have also vaporization processes occurring, tending to make the liquid phase transition to gas phase. So a typical injector nozzle may be on the order of 100 to 200 microns in diameter. Computational cells maybe very, very high resolution would be on the order of 1 millimeter. So you can see that the cell size is already much bigger than the hole size for the injector. So this whole process of what's going on inside this computational cell is just not resolved. We have to provide models for what's going on. So if you think about describing a spray, so we have this collection of droplets here. It's very useful to think of a droplet distribution function, which is a function of position in the spray. It describes the distribution of velocities of the spray droplets, the size range of the droplets. You could add other parameters such as the temperature of the droplets. And of course, this distribution function would change with time. So if you think about it, there's 3, 6, 7, 8. We've got 8 plus time, 9 independent variables to describe what goes on inside a spray. So it's quite a multidimensional problem. If you knew this distribution function and you integrated over all of the independent variables times, say, the volume of the drop, you could determine, for instance, the gas void fraction or drop number density, and using an expression something like this. And we'll see moments of this distribution function appear when we start looking at source terms in the governing equations. The fact of the matter, though, is that current spray models assume that the droplets occupy negligible volume. So that means that you can kind of see that even in this case here, most of the cell consists of gas. There is liquid here, but we are saying that the liquid volume is negligible. And that's certainly true as we move further away from the injector. It becomes a questionable assumption, obviously closer to the injector. But basically, this is the big assumption that most spray models make. The other thing is that, as you'll see on the next slide, a spray consists of many, many droplets. And so one approach that is used is, instead of treating individual droplets, to essentially group them together stochastically. So this was an approach that John Dukowitz introduced that basically made spray modeling possible. It was a major advance. And the idea that he had was this. If we take a look at a typical engine, for instance, that's injecting, say, 160 milligrams of fuel every cycle, and say we have 6 spray plumes, that means that we have 26.7 milligrams of fuel in each spray plume throughout the injection process. If we assume a size for the drops, we can see what the typical droplet mass is. And then using this and the amount of fuel, we can estimate how many drops there would be in the domain. So you can see here there's about 70 million drops, 10 micron drops, that would be created from just one plume of a multi-hole injector. So that's just impractical to track that number of droplets and the processes that occur when they break up and turn into many more droplets and so on. So what John Dukowitz said was, why don't I just group droplets into what he calls parcels? So I inject my fluid, and instead of tracking the breakup and the production of individual droplets, I'm going to assume that I can represent these, this process through essentially a stochastic ensemble of parcels containing identical droplets. So all of these drops that you see here have the same size, velocity, temperature, and position. But I allow it to change from parcel to parcel. So with this approach, when you take a look at a simulation result, you'll see what look like droplets. But in reality, each of these droplets or parcels here consists of many droplets. It could be 1,000 droplets in one of these parcels. So you can see we needed, say, 70 million droplets. But using this approach, if each of these parcels contains 1,000 drops, you can significantly reduce the number of parcels of drops that have to be tracked during a simulation. And typically, we use on the order of several thousand droplets to represent a spray, or parcels of droplets. OK, so that's, I think, one of the major simplifications that was introduced. So now we can take a look at what would be required to implement that spray model in a practical calculation. Starting looking at the gas phase equations. Last time we spoke about mass conservation, and we had a source term on the right-hand side accounting for spray effects. So as those droplets vaporize, they contribute vapor to the gas phase. And we can keep track of that by essentially, if we knew the distribution function of the droplets, integrating over all the droplets in a computational cell and multiplying by the surface area and the vaporization rate of the droplets. So R here is a parameter we have yet to specify, and that's going to come from submodels. It essentially says the rate of change of droplet radius with time. We need to know that in order to calculate the source term associated with vaporizing droplets. Similarly, if we look at momentum conservation, here's our Navier-Stokes equations, which I'm sure you've seen. This term here, F, corresponds to a momentum exchange term between the spray and the ambient gas. And we need to be able to specify that. So if we look at the equation, we have our general viscous and turbulent stress terms, and then this source term, which is the rate of momentum gain due to the spray. So basically, as droplets slow down due to drag, that momentum is transferred to the gas, and this is the term that does that. But we still have to specify what that term looks like. Yeah?
What is the
This one here, I'm sorry, that's the droplet temperature. So in the example I gave you before, we just took a simple concept that the spray would be characterized by these independent variables, and one of them being droplet temperature. You'll see later, we can add to this list of independent variables whatever we want to characterize the drops. Okay. Then looking at energy conservation, here's our energy equation. Again, we saw this last time, written in terms of the specific internal energy, our PDV work term, our flux term involving gradients due to temperature gradients and conductivity, and then species mass fraction gradients carrying with them enthalpies. So that's our heat flux term. We have turbulent dissipation. Combustion, heat release, we spoke about that last time. So here's the extra term, and this is energy due to the spray, and this obviously impacts vaporization, because in order to vaporize the fuel, we have to steal some energy from the gas to do that vaporization process. To supplement all of this, we have equations of state, obviously, ideal gas equation, and then to specify the specific heats, we use data from tables and so on, just like you might expect. Okay, so that's the gas phase. And you saw now we have the source terms, R for rate of radius change, F for the droplet drag terms, and then we have the heat transfer. So now looking at the liquid phase, and again, all of this is described for example, in the Kiva manuals. Here's our distribution function. I've just added a couple more independent variables here. Y, you'll see later, is a measure of the distortion of a droplet from being a sphere. And Y dot is the rate of distortion of the droplet. We'll see that distortion of the droplet changes its drag coefficient. So that's why we need to track that as well. Okay, so here's the spray conservation equation. Essentially, it's a conservation equation for the number of droplets, and was proposed by Williams many years ago. We have a time evolution term, and then we have fluxes in the spaces defined by these independent variables. So for example, here, the droplets are moving at velocity v, so we have a convective flux as this distribution function changes from cell to cell due to droplets being convected from one cell to the next. Here's a term that you need to think a little bit about, because now we have convection in velocity space. So as droplets, say, suffer drag, a class of them will slow down or speed up, depending on the local flow situations, and they will move to a different part of velocity space. So just like you can move in physical space, you can move in velocity space. Similarly, for changes in droplet radius, as a droplet vaporizes, it becomes smaller, so it moves to a new part of droplet radius space. So each of these terms here represents a flux in the appropriate space. Droplet temperature space, droplet sphericity space, and so on. So here are our source terms that we still need to worry about, the droplet drag, the vaporization due to change of phase across the droplet interface, droplet distortion. And then on the right-hand side, we can also change the details of the distribution function through collision and breakup processes. So for example, if a droplet breaks up, its size changes. So it moves to a different part of this distribution function space. And same with coalescence. So here, there's terms we spoke about before, the spray exchange functions. If you look at the drag component, we have a term that is associated with the momentum exchange between the drop and the gas. But then we also have this term here. So as a droplet vaporizes, it is also adding momentum to the gas because that vapor leaving the droplet is a source of momentum for the gas. So we have to account for that in the momentum source term. Similarly, if we're looking at the contribution in the energy equation due to the spray, as the droplets vaporize, here's the surface area times the rate of change of radius, they carry with it a change in the kinetic energy and the internal energy associated with those droplets. Here we have a change in energy due to the change in droplet temperature. As you might expect, the droplet temperature changes again because of heat transfer with the ambient gas, and that needs to be accounted for in the source term. And then finally, we have a work term here, which is basically the drag forces times the difference in velocity between the droplets and the gas. I'm going to talk more about turbulence modeling a little bit later, but this U prime that you see here is an attempt to try to include the effect of turbulence in this work term. So when you look at the turbulence equations, you'll see there's also a source term associated with the work done by the drag forces. And that's this F dot U term here, the drag forces times the fluctuating velocities of turbulence. OK, so that's where the connection between the liquid phase and the gas phase comes about. Now, the question is, how do you solve an equation like this? You saw it was 9 independent variables. We just added a couple more. If you try to solve this using, say, an Eulerian finite difference method, you find pretty soon that you're going to run out of computer, because if you have, say, 100 points in each of these spaces, and you've got 9 or 10 spaces, you've pretty much run out of computer. So the method that's used is to solve the equation using the method of characteristics. So basically, you break the equation into its characteristic equations. Essentially, the idea is that if you want to look at the droplet position change as a function of time, you know that that's due to the droplet velocity in physical space. So here I have a droplet. It's located in a computational cell. This is one of these cells here. In the Kiva code, by the way, the gas velocities are defined at the vertices of these cells. There's a piece of that missing here. Oh, OK. So as the droplet moves from one location to the next, we can predict that movement knowing the droplet velocities. So how do we get the droplet velocities? Well, this is the equation that represents the acceleration of the droplet due to drag forces. So if we can specify these drag forces here, we can then calculate the change in velocity of the droplet. And similarly, we can calculate the rate of change of droplet radius, knowing this source term due to vaporization. OK, so the idea is that we know the position of the drop at time t. We want to predict the position of the drop at time t plus dt. So we can solve all of these equations in order to make that prediction. So in this cell, we also have other things available. For example, from the gas phase turbulence equations, we know the fluctuating velocity in the gas phase, u prime. So a component of the gas motion will also include this turbulent fluctuation velocity. And we also know the length scale of the turbulence from the K epsilon model. And that will show up in some of the models as well. So the turbulence provides L, the length scale, and the turbulent fluctuation velocities. The spray submodels provide F, the drag force terms are the vaporization terms, the collision and coalescence, and the breakup models. And then, of course, we need to start everything off. We need initial data. So at the injector back here, we need to provide the velocity of the drops, their sizes, and their temperatures, and so on. So that would come from the atomization model. Just a brief word on the turbulence. I mentioned the K epsilon model last time. So we've already seen this equation here. The new thing is this term on the right here, which I mentioned before, is the rate of work needed to disperse the droplets. So you saw the spray was spreading due to entrainment. There's also a dispersion process taking place because of the turbulent eddies that trap those droplets. And that's modeled with this last term here. That term also appears in the epsilon equation, the rate of dissipation of turbulence kinetic energy. The other thing that the turbulence model gives you is an estimate of the turbulent diffusivity that comes from K and epsilon. Again, we saw that yesterday. An estimate of the eddy sizes, again, comes from K and epsilon. And, of course, the turbulence intensity itself, we can relate that to the turbulence kinetic energy. So turbulence model is kind of the connection between the interaction of the spray and the gas phase, the work done by the droplets on the gas phase. Okay, so that was a real brief review of the equations that appear in some of the CFD models for two-phase flows and engine applications in particular. I'm going to show you a list of models in a minute, but just let me describe this picture first. So this is what we're after. Okay, we have an internal combustion engine. Here you see it's a 4-valve engine with intake valves, exhaust valves. And we want to resolve in this situation the processes that occur in the combustion chamber, starting with the time when the valves are open. We have intake flow generating swirl, tumble flow fields, and so on. And then we have fuel injection, in this case a 6-hole injector, injecting these what look like drops, but remember they're parcels of drops. Here they're colored by, I guess this is temperature. So the droplets are injected, they vaporize, and eventually the liquid phase is transferred to the gas phase. We have combustion taking place, and then these black clouds that you see here are predictions of soot location in the engine. This is just shown at one instant in time, but of course during the combustion process, all of the droplets eventually disappear, and we have oxidation reactions occurring, so some of the soot disappears. And then at exhaust valve opening, we track everything that's in the combustion chamber and consider that to be the engine out emissions or whatever we're interested in. Okay, so some of the models that we've worked on over the years are shown here. So for example, I just mentioned the intake flow. By accounting for valve motions and so on, one can compute the details of the intake flow motion. This is one of the first things that we did back in the 90s. The heat transfer model, in most CFD applications, you'll see the law of the wall used. Remember I mentioned that the boundary layers are very thin in an engine. 100 microns is a typical thickness. Again, that's much smaller than your 1 millimeter mesh, so you have to use a submodel. Law of the wall would be a candidate model. However, in an engine, the flows are compressible and unsteady, so we have introduced an improvement to the heat transfer model that takes into account those factors, and I'll talk about that. Turbulence models, there's the RNG and recently large eddy simulation models. We're going to be talking about nozzle flow and cavitation modeling in a minute. Atomization, some of the processes that lead to the breakup of the jet. Once the jet is broken up into droplets, we have droplet breakup models, droplet drag, droplet impingement. These are all things I'm going to be discussing today. Collision, coalescence, vaporization. And then we spoke about combustion last time. We'll come back to that probably a little bit tomorrow. And then emissions I'll talk about today. Okay, so let's start with just an overview of atomization work. Here is this is actually out of my PhD thesis many years ago. a description of what happens when you inject a liquid through a single hole orifice. So if you have a very low velocity jet, what you find is a continuous intact stream of liquid. Surface tension leads to instabilities that grow on this jet, and eventually they pinch off droplets here. So this is due to surface tension. You'd see pretty much the same breakup if you did this in a vacuum or whether you had a low gas density environment. This is referred to as the Rayleigh breakup regime. So as you increase the density of the environment, what happens is that as these waves grow on the surface of the jet here, they kind of look like airfoil sections. The dynamic pressure in the gas lowers the pressure at the crest of these waves, which augments the breakup process. So you start to see an impact of the gas density in the environment, which accelerates the breakup, hence the name wind-induced breakup regime. As you further increase the relative velocity between the gas and the liquid and the gas, or you increase the gas density, the wavelength of these waves becomes much shorter, and eventually you see a little intact region here, and I'll show a blow up later, leading to short wavelength waves, which eventually break up the jet. And then finally, in the atomization regime, the breakup length here appears to go to 0, and you start to see what looks like breakup occurring right at the nozzle exit. So most atomization studies, like in a diesel application, are interested in this atomization regime, where essentially the concept is that the growth of disturbances is so fast that they initiate breakup right at the nozzle exit. Okay, so that's what we're headed for, to try to model. But before we can do that, we have to worry about what happened inside the nozzle. So nozzle cavitation is an active area of research because people have found that if they take a lot of pains at designing the shape of the interior of the nozzle, they can prevent breakup completely. So for example, in jet cutting applications, they will use a sapphire nozzle that is very well rounded and no flow separation takes place. And you can get this intact stream at very, very high Reynolds numbers that would normally break up into a spray. And it can be used to cut leather and various other materials, wool board and so on. So it's really what happens in the nozzle to a large extent that determines what kind of spray you're going to get. So cavitation is one of the processes we have to worry about. Cavitation basically is where you have mixtures of vapor and liquid in the flow. And one of the models that has seen a lot of use is the so-called homogeneous equilibrium model, which basically says you have one fluid, but its density can change all the way from the density of a vapor to the density of the liquid. So you can define this parameter alpha here, which is essentially a void fraction, which is 0 if you have pure liquid, and it's 1 if you have pure vapor. And from this equation, it comes from Wallace' classic equation, you can predict the sound speed in terms of the sound speeds of the vapor and the liquid. And this plot here just shows experimental data of the sound speed as a function of the void fraction. You have high sound speeds if you have a pure liquid, high sound speeds, or of course lower than in a liquid if you have pure vapor. And then somewhere in between you see a real reduction in sound speed. And that's because when you have bubbles in a flow, those bubbles basically act like you had a pliable wall in your duct because they're compressible. And so the sound speed, which is dp rho, or in other words, the change in pressure associated with changes in density, becomes very low. So here's your sound speed equation. Knowing the sound speed variation with void fraction, we can calculate pressure as a function of density. So this equation here becomes your equation of state, if you like, to replace your ideal gas equation in your simulation. So this just shows an example where we did a calculation looking at one of the holes of a multi-hole nozzle here. If you look carefully, you can see the needle over here is moving with time. And what I'm plotting here is the flow density inside the nozzle passage or inside the flow domain together with the streamlines. And over here is the velocity, the average velocity across the cross-section at the exit of the nozzle. Notice that you see all kinds of really interesting flows. It reminds you of what happens when you let the water out of the bath, right? As the flow goes down the drain. And that's what you're seeing here as the flow starts up. You also notice that these cavitation regions, which show up here as low-density regions, appear first at the corner of the inlet of the nozzle, and then they extend all the way downstream. Of course, the velocity rises during the startup, and then you see the falling velocity and the cavitation region going back to the nozzle. So what you get from a calculation like this is essentially the injection velocity as a function of time, and also information about the density of the fluid exiting the nozzle, which can be used to verify simpler models. So here's an example of a simpler model that is used in many of the CFD codes that we run. Basically, here you have your reservoir supplying flow. It enters, in this case, a straight hole nozzle, but with an entrance radius of curvature. There is a separation that takes place at the so-called vena contractor here. That's determined by this contraction coefficient, and there's experimental data available to tell you how that contraction coefficient varies with the radius of this entrance radius to the passage relative to the diameter of the hole, ranging from a sharp edge hole up to a fully detached flow. So this cavitation region, as you saw in the movie also, essentially can extend all the way downstream. And what we're interested in is the effective diameter of the jet when the jet leaves the nozzle. It's not necessarily equal to the nozzle hole. And also the effective velocity of the flow. So how do we predict cavitation? Well, essentially there's this parameter psi here, which is related to the contraction coefficient that tells you, and looking at the pressure downstream and upstream, whether you have a non-cavitating or a cavitating flow. As I mentioned, typically you have cavitation to worry about. So in this case, we will go into in the code, we'll go into those equations, find this psi parameter, decide whether we have cavitation or not. For the case with no cavitation, the discharge coefficient, which basically modifies the Bernoulli equation here for the injection velocity, is a function of the passage length because of the friction at the walls. And the effective nozzle area is essentially the actual nozzle hole diameter squared times pi over 4. So for no cavitation, this is pretty simple. For the case with cavitation, we see the discharge coefficient now depends on that contraction coefficient, and also this cavitation number, which involves the vapor pressure and the pressure difference across the nozzle. The effective velocity can be calculated, and then the effective cross-sectional area of the nozzle can be calculated. So again, these types of simpler models can be verified with those detailed simulations that I showed you. Okay, so once we have the diameter of the nozzle and the velocity, we can start looking at the atomization process. Here I'm talking about the model that's called the wave breakup model. Basically, the idea is here's that intact portion of the jet that I showed you in one of the pictures earlier. You can see evidence for short wavelength waves that grow on the surface of this jet. Using a linear stability theory, we're able to predict the wavelength of these waves and the growth rate of the waves, and hence the local wave elevation or amplitude. So the wave amplitude then is a function of an initial amplitude times an exponential or sinusoidal function of distance, z, from the nozzle, a wave number, k, and omega being the growth rate of the waves. And the idea of this theory is to relate the wavelengths to the growth rate. Also, I should just mention the wavelength is related to the wave number k here. So that's the idea of the theory. And just to kind of outline how this linear theory works, we assume that the surface wave elevation, eta here, is the expression I showed you before. So this equation of the liquid surface in our RZ coordinate system here is that r equals a, which is the radius of the jet, plus eta, the elevation due to surface instability. And we linearize the equations. We have, for example, the linearized continuity equation for the velocity components in the z and the r direction. Then we have linearized equations for the momentum in the axial direction is this equation. Notice this capital U here. Capital U is the relative velocity between the jet and the gas. So, for example, if the gas is stationary and the jet is injected at velocity u, the jet velocity, then the relative velocity between the jet and the gas is capital U. Of course, there could be a boundary layer that exists, as I've shown here, but I'll show you in a minute that that's typically neglected in these analyses. So the radial component of the momentum equation is shown here again for the radial velocity component. Here's that U again. And typically, if the gas is assumed to be inviscid, which is actually not a bad assumption, then the boundary layer between the liquid interface and the gas can be neglected, and one can just replace the relative velocity with a constant, which is the injection velocity. Okay, so if one goes through these equations, one finds that the gas pressure can be determined, and it's related to the density of the gas, rho 2 here, 2 being the gas identifier, 1 being the liquid. So the density of the gas, U, the relative velocity between the liquid and the gas, which is, as I said, the injection velocity, and then the phase velocity, omega over k, and then some Bessel functions. So that's what all of this analysis gives you. And then finally, you go to the boundary conditions that apply at the interface, the kinematic, tangential, and normal stress boundary conditions. And essentially, they provide extra constraints. The first one is that the rate of change of surface elevation must equal the velocity in the radial direction. So that's the kinematic condition. If we assume that the gas viscosity is 0, then the tangential balance gives you a relationship between the velocity components in the liquid. And then finally, the most important equations in the box here. This is the normal stress balance. So you can see the pressure in the liquid phase and the pressure in the gas phase. Of course, if you didn't have any viscosity effects or surface tension effects, they would have to be equal. But because we've included the effects of the liquid viscosity, there's a normal stress due to liquid viscosity. And then surface tension is applying another force at the interface that appears in this normal stress balance. So when one plugs this expression here for the surface pressure in the gas phase into this result and then applies these boundary conditions, you come up with what's called the dispersion relationship. Very complex looking equation here that relates omega, the growth rate of the waves, to their wavelengths, k, or wave numbers. It involves Bessel functions. Here you see the liquid viscosity term, that's kind of a damping term. Here you see the surface tension term. And then here you see essentially the forcing function, which is the gas density over the liquid density ratio times the dynamic pressure term, U squared. So this dispersion equation actually is very rich because it describes all of those regimes of breakup that I discussed before. For example, if there's no effect of the ambient gas, you can throw away this term. If you throw away viscous terms, then you just get Raleigh's result, which is shown over here. When Ka is greater than 1, you have a regime change from long wavelength waves to short wavelength waves. So all of that shows up in this dispersion relation. If you take this equation and non-dimensionalize the parameters so that you plot a non-dimensional wave growth rate against a non-dimensional wavelength, non-dimensionalized with the radius of the jet here, you get these type of curves that are a function of 2 parameters. The so-called Weber number, which is based on the gas density. We'll talk more about that in a while. And then the Onsauger number, which is essentially a ratio of viscous forces to surface tension forces. So when you have a highly viscous jet, you'll have non-zero Unsauger number. Generally, the Unsauger number is kind of small. So if we assume zero Unsauger number, what these plots show you here in the solid lines is what happens when you change the gas density-based Weber number. Weber number is the ratio of the dynamic pressure term, rho to u squared, essentially, divided by the surface tension term, sigma over A. And as you can see, as you increase the Weber number, you're essentially driving the wavelengths, the most unstable wavelengths, to shorter and shorter wavelengths. And of course, the most unstable wave growth rate increases significantly. So this really explains what we saw before. Very high velocity jets are going to lead to very short wavelength waves that break up very fast. So the linear theory captures many of the aspects that are known for jets. And you can essentially characterize this whole process by looking at this non-dimensional wave growth rate and wave length. So we've done some curve fits of those solutions and come up with these expressions in the wave breakup model. So here's the non-dimensional wave length, and here's the non-dimensional wave growth rate. Function of essentially three parameters here. The Weber number that I just spoke about, the gas density, the velocity, injection velocity squared, the radius of the jet, and the surface tension. And then the Unsauger number, ratio of the Weber number and Reynolds number in the liquid phase. And then finally Taylor's number, which is Unsauger number times Weber number. And if you look at these curve fits and compare them with the theory, you see we do a very good job here. Here I'm plotting the non-dimensional wavelength against the Weber number. Symbols are the results of this curve fit. The lines are from the complete theory. And you can see that, as we said before, if we increase the Weber number, the wavelength decreases. This is a log plot here, so it's a significant decrease in wavelength. If we increase the Unsauger number or increase the viscosity, the wavelength also increases. If we look at the wave growth rate here, you see similar, as you might expect, as I increase the Weber number, the growth rate increases. And as I increase the Unsauger number, the wave growth rate decreases due to viscous damping effects. Okay, so now we have that theory. How are we going to actually apply it in a spray model? So we have these waves growing on the surface of a jet. We know their wavelength, and we know their growth rate, or breakup time, we're going to say, is somehow related to that growth rate. The size of the drops, we're going to assume, is somehow related to the wavelength. So there's going to be some constants in this model, all right? It turns out that this constant here, which relates the drop size to the wavelength, doesn't really affect results too much. But the most important one is the constant that relates the breakup time to the predicted growth rate. And so in the spray models, there's typically a constant that is varied, and it has to be changed basically to account for some of those cavitation processes that we saw in the nozzle that essentially excite or initiate the growth of these unstable waves. Okay, so the other thing you can get from this theory is an idea of the spreading rate of the jet, because basically if I know the radial velocity component and the axial velocity component, I can relate those again through a constant A here. And it turns out that the spreading rate is dependent on the ratio of the gas density and the liquid density times a function of Taylor's number. This function here is typically just a constant at high values of Taylor number, which is typical for diesel injectors. So what this tells you is that the spreading of the jet is really related to how dense the gas is compared to the liquid density. And this constant A here, again, there are expressions in the literature that tell you how to select that constant. The other thing that you can get from this theory is an estimate of how long it would, what distance it would take from the injector to the point where you've completely broken up the jet. Because we know how many drops or how much mass is being shed from this jet. And in fact, Taylor predicted this in the 1940s, that the breakup length of the jet is related to the radius of the jet, again times this gas or liquid gas density ratio and this function F here, which, as I said, is roughly a constant. So you can see if I have a low gas density, like a vacuum, this theory says you don't get no breakup because the breakup length is infinite. On the other hand, if I have a very high gas density, like in a diesel engine, this breakup length is relatively short. Okay, so is there any evidence for this type of model? Well, you know, the models were developed back in the 70s and 80s. There's been a lot of work recently done, for example, at Argonne National Labs with the synchrotron, where they have used X-ray images to look at these jets. And here's an example. It's a single-hole nozzle. Here's the needle again. And you're seeing X-ray pictures of the jet emerging from the nozzle at different injection pressures. Looking at the very close distance, 0.4 millimeters from the nozzle exit in these pictures. And if you look carefully, you can see that there is some sort of evidence of instability waves that eventually lead to the breakup of the jet. So we take this to be at least confirmation that this concept, which, remember, you can't see inside a diesel jet, right? It's, as I showed you in some of the earlier pictures, you really don't know what's happening. But with the X-rays, you can kind of get a feel for the fact that surface waves seem to be involved. So that was very encouraging to have a theory that is more or less validated 20 years later. Yes? Okay.
Oh, sorry, I had a question about 2 slides ago.
Okay.
Question. So for this spray angle, that only enhances the liquid phase, not the
So this essentially tells you in the model what radial velocity to give the droplets. We know the axial velocity that we got from our nozzle cavitation model, but now we need to know the radial velocity. And so that's what this spray angle tells you.
So that's
Only for the liquid, yeah.
And then my other question was for the breakup length.
Mm-hmm.
There seems to be like a physical correlation for the breakup length, yet that's an input to keep it that you can change and use the tuning constant.
So I'll tell you how we do that in a minute, yeah. But basically, what I'm describing here is what is called Kelvin-Helmholtz instabilities. I'll show you that there's some evidence that we have to worry about other instabilities. And they occur further downstream when the spray droplets are already formed. Okay, thanks for the question. Okay, so droplet breakup. This is an area that's also been looked at for many, many years. The mechanism of breakup is quite misunderstood or poorly understood. And it turns out that there's several breakup regimes. So here's a droplet that's exposed to a gas, and it's just a conceptual picture of the breakup of that droplet that you'll find in many early publications. For example, Hinze and work in the 50s argued, kind of like we did here a minute ago, that breakup is due to capillary or surface tension induced waves on the surface of the droplet. Then in the 60s, during the era of rocket simulations, there was a lot of work done, especially at Michigan, where they argued that the breakup was due to what's called boundary layer stripping. The argument is that you have a boundary layer that develops due to viscosity effects on the gas that leads to essentially momentum transfer between the gas and the liquid, and that leads to breakup. And in fact, Professor Surignano and his group developed a theory and published it in the 90s, where essentially they calculate the thickness of this boundary layer and argue that the drops that are formed is somehow related to that boundary layer thickness. I'm going to show you that we published some work a little bit after that that presents quite a different picture to some of these theories that we call the stretching and thinning breakup mechanism. So let me explain how we came about that. We did some experiments where we have a very nicely contoured nozzle that produces a very flat velocity profile at the exit of this nozzle. So we have gas flowing through the nozzle. And then on the side here, we have a Berglund-Lou droplet generator that creates a monodispersed stream of droplets. They all have the same size. And these droplets then interact with this well-characterized gas flow and break up. So what we can do then is change the gas velocity, the droplet size, and so on, and take a look at the breakup process. So here's some pictures. So here's the droplets coming in from the left here and interacting with the gas. These are high magnification pictures. These droplets are on the order of 100 microns in diameter. And you can see that for relatively low Weber numbers, the droplets flatten. And that's because, if you think about it, as they encounter this gas flow, this used to be a spherical droplet. You can see it just started to interact with the gas flow. There is a stagnation point at the north pole of the droplet where the pressure is higher and you have a flow around these droplets. And at that stagnation point, the droplet is flattened. And you see it becomes flattened here. As you increase the velocity of the gas, you're increasing the dynamic pressure. The droplet flattens more, and in fact, it can turn inside out and create this so-called bag breakup. So you get this thin membrane that forms around like a donut, or it's inside the donut. Okay, so that's what happens at low jet velocities, or gas velocities. But if you go to the other extreme, where you're now looking at very high jet velocities, or gas velocities, and by the way, the relative velocity in this case is more typical of what you would see in a diesel application. You see these type of pictures. So here we took those same pictures. Now those drops are actually coming in from the right. Here's the drop before it encounters the air. And these are double pulse pictures. The exposure duration was very short, a couple of nanoseconds. And so you can kind of see a blur here. That allows you to calculate the velocity of the drop, for instance, if you were interested. But here is two pictures, or again, here's a drop. But here are two pictures, or pictures of drops taken at these two instances in time that show basically the development of the flattening of the drop and then development of surface waves on the surface of that drop that eventually lead to, I call these strands of spaghetti. And so we wondered what would be the explanation for this. And part of it turns out to be we think, due to the appearance of Rayleigh-Taylor instability. So Rayleigh-Taylor instability is this thing that happens when you take a cup of water and you turn it upside down. All right, you'll see that the surface doesn't stay flat, but it develops, good, the lid was on, develops an instability wave. Well, the reason for that is because the liquid is being accelerated by the force of gravity. Well, here you're accelerating it because of drag effects. And the accelerations that these droplets experience is in the millions of Gs. So this acceleration leads to an instability at the surface of the jet, which can be calculated from Rayleigh-Taylor theory. The Rayleigh-Taylor theory predicts the wavelength of those unstable waves in terms of the acceleration, or which would be a negative number in this context, and the surface tension, and also the growth rate of those instabilities. So the drop stream comes in here, is hit by the air, the droplets flatten because of that dynamic pressure effect. They accelerate drastically. The acceleration leads to the formation of these Rayleigh-Taylor waves, which then essentially snap off pieces of the jet, which then are subject to the Kelvin-Helmholtz waves that we discussed before. And we think that this is a reasonable explanation for what you're seeing here. Combination of two breakup agencies. So to kind of summarize droplet breakup phenomena, you can see we're going from the flattening of the droplets. This occurs at relatively low Weber numbers. These Weber numbers are based, I don't think I said it yet, are based on the gas density. And then eventually what we're calling catastrophic breakup for very high Weber numbers. Okay, so droplet collision and coalescence modeling. Peter O'Rourke was essentially a pioneer in this area. He borrowed heavily from the kinetic theory of gases. And he said, okay, I have these two droplets. They're going to collide just like molecules collide in a gas. I can look at the kinetic theory and see what are the parameters. I want to calculate a collision frequency between drops in parcel 1 and parcel 2. I know how many drops there are in parcel 2 here, let's say. I also know the effective collision diameter. So basically, knowing the radius of drops in parcel 2 and in parcel 1, I can calculate, like we do in kinetic theory, knowing essentially the collision cross-section of two molecules. I also have this so-called collision efficiency term, which says that if you take, for example, a small droplet and you let it approach a larger droplet, it may just bypass that because of fluid mechanic effects. They have to do with this function down here, which involves the gas viscosity. Typically, though, for the droplets of interest in sprays and the gas viscosities that we're interested in, K is large, and so this collision efficiency is taken to be unity. And then finally, we have the vector difference between the droplet velocities and the volume of the cell in which these droplets are located. So that's a calculation of the collision frequency. So in order to use this in a stochastic simulation, what Peter O'Rourke did was to say, all right, let's consider this to be a Poisson process. The collision frequency is shown here. The delta T would be the time since the last collision of droplets in that cell. And what we're after here is N, which is the number of drops in parcel 1 that are going to collide with drops in parcel 2. And to make this possible to calculate, we need the left-hand side, which is essentially taken to be a random number between 0 and 1 in this Poisson process. So one picks a random number, and that gives you then N, which tells you essentially how many collisions took place during that time interval, delta T. OK, so we've had some collisions. Now, what happens when those drops collide? Well, here is a picture showing those droplets colliding. We've got small droplets colliding with big drops. The small drops are moving in this direction, big drops in that direction. This is the relative velocity vector here. If we define essentially the distance between these two drops at the moment of impact as using this quantity, the impact parameter, essentially it measures the distance between the centers in this orientation. We can plot impact parameter versus Weber number. So what does the impact parameter mean? If it's 0, we have a head-on collision. So drops are just colliding head-on. But if the impact parameter is unity, the droplets just slide past each other and just barely graze and touch each other. So impact parameter is a very important measure of just the orientation of this collision process. It's normalized here by the sum of the diameters of the or the effective radius, if you like, of the collision. Another parameter is delta, the ratio of the drop sizes of the small drops and the large drops. And then again, the Weber number, and that's what's shown on this axis. Now it's the Weber number based on the liquid phase that's important, liquid phase density. Well, it's a very busy looking plot, but this shows experimental data that essentially try to group the outcome of these collisions in terms of what is seen experimentally. Reflexive separation, I'll show you pictures of these in a moment, but basically the droplets basically bounce off each other like you would have in the case of a tennis ball hitting a surface, because these are like head-on collisions. B is small over here. Then we have this so-called stretching separation regime. And here's a picture that shows that here, where we have droplet streams colliding, the droplets merging, and then because of the energy associated with that collision, forming essentially a train of ligament droplets in between the parent droplets as they separate. This is your stretching separation. I've got some better pictures I'll show you in a minute. And then the bounce regime here has to do with when the droplets are just sliding past each other and they trap gas in between the two droplets and then fly apart. And then finally, the green here is the coalescence. This is the part where two droplets become one droplet. OK, so some really nice pictures from a JFM paper by NASA Ashgress and students. It shows over here a colored stream of droplets. This one is, these are water droplets colored with food color. Here's the red drop. Here's the uncolored drop. Here we have impact parameter of a half, Weber number 10, and they have the same size, so delta is 1. And you can see here that basically these drops are going to coalesce. Notice how they're kind of rotating. The red goes to the bottom and then comes back up to the top again. If that rotation is, the energy associated with the rotation is enough to overcome surface tension, these will fly apart again. But in this case, they coalesce. And there's a theory that describes whether this rotational energy exceeds the surface energy, and it leads basically to this result, where we have the size ratio of the droplets, the Weber number, and the impact parameter. So how do you use this in a CFD code? Because all of this is happening subgrid scale, right? We're not modeling any of this stuff directly. We use the idea that there's a stochastic process. We pick a random number that gives us the impact parameter, and then we check to see if this is satisfied. If it is, we go back and take a look and see which regime we're in, and if it's in this coalescence regime, then we use that result. This is just an example of pictures showing the stretching separation. Again, I showed you this earlier, but here much nicer pictures. You can see again the red drop at the top here, but it's rotating around. You see a flattening and extension of the liquid, and eventually a formation of individual droplets. So here we have stretching separation. In this case, there were no satellite drops formed in between. But we have a theory that we've used to account for that as well. And then finally, the reflexive separation. Here we have these two drops colliding head-on. You see really interesting structures. The red stays at the top here, so it's like a tennis ball bouncing off the other droplet. Okay, I have to hurry a little here. So to summarize, yeah.
Just a quick question. So you're tracking each parcel, and then whenever two parcels come close enough together, at that point they're assigned a random impact parameter?
Right. So actually we do it this way. We found that the results of these collision models can be very sensitive to the mesh size. If you say that I'm just going to look at the droplets in a particular computational cell, which is the original formulation that O'Rourke had. So if you just say, I'm going to take the drops in a computational cell, decide whether they're going to collide, calculate a collision frequency, and then for those that collided, see whether they coalesce or break up and so on. So what we do now instead is we use what's called a radius of influence collision model, where we decide that we're going to take a group of cells, but we're always going to use the same radius of influence. Typically, it's on the order of several millimeters. And then look at all the drops inside that radius of influence, check whether they can collide using this stochastic idea, and then the outcome of the collisions is calculated.
Has it been reestablished like a new packet, like because you said originally?
Exactly, yeah. So, and that's great because essentially you're reducing the number of parcels when two of them collide. Or you can just simply change the number of drops in one parcel versus in the other, depending on the outcomes that you have here. The other problem is when you have breakup, because now a parcel can produce many more droplets. And if you make a new parcel and you add that to your already thousands of parcels, pretty soon you can have problems with computer storage. So you have to be a little careful about how you assign new parcels in a simulation. But we've worked through that as well in some of these spray models. So, yeah.
Well, my guess is these experiments are carried out at about room temperature.
Oh, yes. Yeah, this is just in a lab.
You're looking at close compression temperatures and maybe looking at about 900 Kelvin. So
absolutely. So we have to worry about vaporization on top of all of this. Yeah, and drag forces. All of that is included in the models. Yeah. But these experiments just isolate the collision process. All right. Yeah.
So do you have any, or do any of these models include collisions within parcels, like for all the droplets that are like all within a particle?
Yeah. So basically, let me just go back to. Maybe I didn't explain that well enough. If I go back to this slide here, I'm interested in how many of these droplets in parcel 1 are going to collide with the N2, is the number of droplets in parcel 2. How many of these droplets will collide with N2 droplets in parcel 2? So that's what my N was over here in this Poisson thing here. I assume the left-hand side a random number. I know the collision frequency. and I know the time interval between when the last collision occurred and now. That would be my numerical time step. And I can now calculate n. So that tells me how many of these droplets I'm going to allow to collide. And then I make an adjustment to the number in this that I leave untouched. And the rest of them, I go through this exercise of determining what kind of collision outcome to expect.
So what I guess what I'm asking is, rather than looking between, I understand this is between two sets of two different parcels, the droplets between two parcels. What about within a parcel? You have this collection of droplets that might interact with each other.
We don't do that. Yeah, I mean, ultimately you'd like to do that, but that would be the next level of sophistication. Yeah.
Just one last
Mm-hmm.
question. About the application of the collision theory here, you would have to deal with the fact that there's still an interaction of molecular forces interact before they get into contact. Do you be able to take them?
You mean like a Lennard-Jones interaction?
Yeah.
That's kind of in this collision efficiency term here. Because, essentially this accounts for the flow field effects as the droplets approach each other, whether they actually are going to collide or not. But typically, because the gas viscosity is so low, this number is typically unity. Thanks, that's a good question. All right, I'm just going to show the last slide, and we can take some more questions for this section. So this approach that I've just shown you here is called the discrete droplet model approach, or the Lagrangian drop Eulerian fluid approach. So we track the droplets using Lagrangian coordinates. The gas is solved using the Eulerian field equations. And basically, you'll see this in pretty much all two-phase flow codes, especially for engine applications. It's in Fluent and many other codes that are also used for two-phase flow modeling. So some of the models are quite detailed now. They're available for engine CFD codes. They provide a description of what happens in the nozzle flows, the effect of the liquid and gas properties on spray formation, and the drop breakup physics, as we've discussed. But due to the importance of sprays, a lot of research is still needed. And in fact, if you attend meetings such as ILAS, the Atomization and Sprays meetings, or ICLAS, lots of papers in atomization sprays are dealing with these very topics: how to improve the collision models, how to improve breakup models, and so on. So there's a lot of progress being made. LES and DNS spray modeling. Here's a picture. Mario Trujillo is one of our group, has been doing DNS simulations of breakup of liquid jets. You can see his models are able to predict the breakup process. Well, now we're trying to see how accurate are these. And we need detailed experiments to be able to measure these droplets. Again, in a dense diesel spray, those experiments are really difficult. So he is actually working with the group at Argonne Labs to try to compare some of his DNS simulations with those measurements. So there are other methods for doing experiments. I showed you the X-ray imaging, ballistic imaging, large eddy simulation. There's some work being done there, and of course DNS. So very active area, and it's active because, as we can imagine, the spray is basically what sets the stage for the combustion process, right? The mixture of the fuel and the air is really determined by the spray. So a lot of work is still needed there, and if anybody's interested in doing spray research, I totally encourage you to do that. Okay, questions? Yeah, let's start with Bill.
In the literature, I've seen papers refer to primary atomization.
Right, that's what this is here. Basically, the liquid, as it first enters the chamber, and its first breakup is called primary, but now you have droplets formed that can undergo secondary breakup. Huh? Yeah.
My question has to do with the relation with the random model and the stochastic models. So these stochastic models have these random numbers, and you have turbulence, which is disordered, but it's then average.
Right.
So how can you use these two different sort of models?
Okay, so that's really attacks the heart of stochastic models. Essentially, you want to say, I'm going to represent some kind of average process. I'll use rants to give me an idea of what the turbulence looks like, and we're going to be talking more about the turbulence a little bit later, because we can treat that also stochastically. And then with that stochastic representation of the turbulence, I'll now see what the impact is on droplet breakup, collision, coalescence, and so on. Ultimately, one would like to do a first principles model, but you know, when you talk to people about DNS, there's still an argument about whether you can do DNS with sprays, because you've got to resolve the flow inside each droplet. The droplet is 10 microns in size. So you need, you know, 100 mesh points or whatever inside a droplet, and you've got 10 million droplets. It just becomes impractical. At some point, you have to simplify the problem.
Yeah, I was curious about how they treat the fact that I think most fuels are actually mixtures of different volatile species with different volatilities. And a really interesting phenomenon I saw was microexplosion.
Oh, yeah, yeah.
Where does that fall into the regimes that we see on slide 27?
It's not there at all, yeah.
Is it just that
So if you have emulsions, and there's, you know, there are models in the literature. Professor Lee at Urbana-Champaign has published a number of models on that account for nucleation processes, microexplosions. But again, they are pretty gross, simplified models. But they do exist. Yeah. I didn't include them here. Yeah.
Earlier in the lecture, you went through Lagrangian drop liquid phase modeling, and you said drop size was modeled as dr ODD equals R.
Right, so that's for a vaporizing droplet, and we're going to talk about that next.
Is this approximation similar to the d-squared law for
Absolutely.
vapor evaporation?
Yep, we're going to see that when we talk about vaporization. Yeah. Yep.
Do you have any idea about, so when you take all these many millions of droplets and coalesce them into parcels for say computational reasons, do you have any idea about, or a sense of what kind of loss of accuracy that gives, or like what that might impact by doing that, or you can't get possibility?
I'm going to show you, you know, the best we can do is to compare pictures of sprays and also measurements of drop sizes within sprays with what these models predict. And I'm going to show you some of those results a little bit later. There are other things that go on, though, numerical things, which I'll also talk about. So this is not the whole story. Okay.
I had a couple of questions on the flow within the injector nozzle. I was wondering how sensitive that is to the temperature of the wall of the nozzle itself.
I'm not sure that anybody has really done a systematic study of that, but you know, the vapor pressure is a factor. You saw we needed the sound speed in the vapor, for instance, which I guess will depend on temperature. So yeah, and of course there's heat transfer in the nozzle itself. I don't know of anyone who's looked at that.
But what temperature profile would one typically assume for the wall of the nozzle?
Yeah. So in the homogeneous equilibrium models, people usually throw away the energy equation altogether. And they assume that you can deal with this by just looking at mass and momentum. One of my students is actually working on an improvement where he actually includes the energy equation as well. And hopefully that would allow us to look at factors like you've described. But if you look in the literature, most people do not use the energy equation in these type of simulations.
Sort of a related question is, do you assume turbulent flows within the nozzle as well?
Yeah, so that's also something that I struggle with, because you know, anyone who studies turbulence knows you need a certain development length before turbulence becomes important. So if you didn't have any cavitation, it would be very hard to justify using a turbulence model. But since cavitation is basically boiling, you've got a lot of disturbance that's going on, and so I think there is some justification to use a turbulence model. Whether you can use the same kind of turbulence models that we use for, say, a single-phase gas flow or not remains to be seen, but that's what we use.
Maybe just an unrelated question. I see a lot of the work you provide here, published as SAE paper. Yeah, it's quite good for us to get access to this lecture. And normally you do combustion research, you get a lot of the chemical genetics and a lot of the other stuff. You don't get connections to nature because most universities don't have access to SAE.
Mm.
You have a comment on that, how that is changing in the future.
Yeah, that's. I don't know how to deal with that other than for you to convince your university, because SAE is very widely. It is the very widely spread form of forum for this type of work. It's engines, right? So Society of Automotive Engineers. So in fact, in some cases, it's hard to get this type of work accepted by the mainstream journals like Journal of Fluid Mechanics. You try to send them an engines paper, they won't accept it. So that's one of the reasons we actually started our own journal. It's called the International Journal of Engine Research, which is a peer-reviewed journal and so on. Whereas SAE is kind of a borderline between commercial and archival papers. So yeah, that's a problem. Well, we only have 15 minutes left for the break. Happy to answer more questions, but maybe we need a bathroom break or coffee. All right? See you in 15 minutes.